Okay, let's get started. So welcome everyone to another lecture as part of our ID 5130 parallel scientific computing course. Okay, so in today's lecture we're going to look at a little bit more on the scope of variables, as well as about a closer look at the parallel, or basically about a closer look at the loops, okay, with a few examples. All right. Okay. Okay. So coming to the scope of the variables. So in the last lecture, we looked at calculation of pi, right, where we had several terms, right. One was there is a term called sign, right. So we used this variable sign, and we had to make this sign as a private variable, right. Otherwise, this was being updated by all the threads at the same time. So we had to make it private. So let us take a look at the corresponding code, what we have looked at in the last lecture. So if I pull that code up here, so we have basically a for loop, right, for k equals 0, k less than, and k plus plus. And then if it is a even term, then we have a plus for the sign, and if it is odd, we had a minus, right. And then the total sum was calculated using sign divided by 2k plus 1, and finally we multiplied it by 4 to get the value of pi. Okay, so what we did was we had to make so hash pragma OMP parallel for, this is all the regular thing. Then we have number of threads, and thread count is the number of threads that is executing this parallel for. Then we said, of course, we have to have the reduction operator is plus, and sum is the reduction variable. Then we made private sign, right. Now of course we did this, but this was we had to do it because initially we ran it without the private sign and we were not getting the correct answer. Then we said, okay, we'll make this sign as a private variable. Okay, so a sign was of course defined kind of defined here, right, before the block has started. That's why the scope for this has to be made private. If it were defined inside, then it would have been automatically a private variable, right. So any variable that is declared inside the parallel for would automatically be created on the thread's own stack. So as a result, it would be private. Okay, so the idea here is that now, of course, it is not a good idea to do this kind of trial and error. See, okay, the program is not giving the correct answer, then look at the variables which are what will be the scope of the variables. Rather, what we should do is we should try to explicitly specify the scope of the variables. Okay, so basically what we should do is we should basically explicitly specify the scope of the variables in OpenMP, rather than doing this way. So essentially what we want to do is we want to explicitly specify the scope of the variables, or scope of all the variables that are declared outside the parallel block. Okay, parallel or parallel for block. Okay, so essentially what we want to do is we want to declare that, and OpenMP allows for that using something known as a default none clause. Okay, so what we can do is we can specify that none of the variables are, like, essentially do not take anything as default. Rather, all the variables will be the scope of all the variables will be declared. Okay, so as a result, essentially we will end up with writing better code, because now we will specify the scope of each variables. As a result, we will not get a different behavior than what is intended. Okay, all right. Okay, so if that is the case, then what we should do is essentially we can say that we would specify using default variable. So we say default none, okay, and then here in this particular case we have how many variables do we have? We have k, we have sign, we have sum, right? So we have and then we also have n, but n is actually not defined as a variable because n was defined as a hash defined. So this is basically n will be substituted for 1000, okay. So 1000 will be substituted for n. So as a result, n is not a variable. But if I were to declare this as let's say an integer instead of a hash defined, then n also will be a variable, isn't it? Okay, so I just defined now as one added extra class. Extra class is basically default none. Now we say default none, and then I would not, let's say, specify what is this variable for sign. Okay, I would just leave it like this and then try to compile this program. So this is okay, so I would just specify gcc minus of OpenMP program pi.c. okay, now it gives an error. So OpenMP, now because that we have added the default none clause to the parallel for directive, it says that sign not specified in enclosing parallel. So this is basically something that is coming from OpenMP, right? Because to check that, let me just basically do it this way, right? It just compiles if it is a sequential code, and if I put it back in, then we get the error. Okay, all right. So basically now we have sign equal to 1. So it says error enclosing parallel because it is sign is not specified. Okay, so that means we have to specify what is the scope for the variable sign. So that is basically private sign. Okay, now of course k by default, although we are not specifying anything for k, but k is the index for parallel first, so that will be taken as private or shared. It will be taken as private. So we can, so it's always a good idea to specify that. But even if we don't specify this particular loop variable, OpenMP would not compile. So I would say, I would let me first leave it like this and then try to compile. Okay, it compiles fine without any errors. Now if I put in k there, this is anyway already private. Now sum is a reduction variable. So something that is reduction variable is has a scope of both a private as well as a shared, right? So sum being a reduction variable has scope of private and shared. Okay, I think for some reason my pen is too thick. Let me fix that and resume the lecture. Okay, so sum being a reduction variable, it has the scope of both private as well as shared, whereas when it comes to the other variables, for example k and sign, they have to be specified as private. Okay, all right, so then this should compile without any, yeah, I mean we have just compiled it. I think this compiles fine and then runs and gives correct answer, a.out5. okay, we got some value for pi. All right, now let us say if I will make n also as a, instead of a hash defined, I would also make n as an integer. Okay, so I would say int n, I would give some value for n. Okay, and then of course I don't have capital N, so I need to make this a small n, right? Right, that should be fine, I guess. Compile. Okay, now again there is an error, right? It says that basically error n is not specified in the enclosing parallel. Well, that means that again it needs to know whether n is a private variable or a shared variable. Now n being not updated within the parallel for, it can be safely made as a shared variable. Okay, so what we can do is we can make it as a shared n. Okay, so that's basically a shared variable and it should run and give an answer. Okay, so that is how you would specify using the default none class, and that would help you in terms of in writing better code, because you would be then specifying the behavior for each of the variables. Okay, so need to explicitly specify the behavior of each of the variables. okay, or the scope of each of the variables. All right. Now let us also look at depending on the in the context of scope. Let us see what will be the values that will be available for each of these variables when we try to use private or shared variables. Okay. So for that I have another code which is called program private variables. So this is basically a small program to demonstrate the scope of the private variables. So what we have is we just again read the input arguments, okay, in this section, and then we have a variable x that is declared before the parallel block, that is basically x equal to 10 is initialized. Then I have hash pragma OMP parallel. There is no for loop, it's just a parallel block, and then we have num threads thread count, and then I have int my rank, where my rank is filled with the rank of the processor, okay, depending on whether you use OpenMP or not, and then it's going to print values of x. So print values of x, that means we have already initialized it here, okay. Then it is being the value is being printed, okay, here within the for loop, within the parallel block, and then x is being again initialized to some value which is my rank times 10, and its value is printed, and then once you exit the pragma OMP parallel, again its value is printed. Okay, now let me make the variable x as a private variable. I would make private x, and because we have just learned this thing, we would also add default none. But anyway, there are no other variables, so default none should not complain. I mean, if I remove private x, it would complain. It will say what is the scope for this one, what is the scope for x. So let me gcc compile this, OpenMP program private variables.c. Okay, it compiles. X is not specified in enclosing parallel. Okay. All right. So I would say private x. All right. Then it compiles fine. Okay. Now let me print this value. So I would like to, let's say, run this with maybe 4 cores. Okay. Okay. It has now printed, but again, as you can see, this is not in any order because it's printing before initialization, after initialization, and so on. Because now the thing is, every thread is competing to write it to the standard output. Okay. But what we see is that x is being initialized to 10. But its value, once we enter the parallel block where it is declared as private, so different x will be created for different threads, right, within the parallel block. As a result, the scope of a private variable as soon as it enters the parallel block is, or the value of the private variable is unspecified within the parallel block. For example, before I initialize it to x here in the parallel block, if I look at what is the value before initialization on different things, on different threads, what we have is on thread 82 before initialization x is 0, right? Although we have set it to 10, it is not correct. And then before initialization 1 is also 0, and it is 0 on 0 as well as on 3. Okay, so that's what it is. And then the value of then once we initialize it to my rank times 10, here x is basically being a private variable, and it's being initialized here, so its value is now defined, and this guy after initialization will print the correct values. For example, on 0 1 2 3 there is going to print 10 times of that. So is that what is being followed? Yes, for thread 2 it is 20, for thread 3 after initialization is 30, similarly for thread 1 is 10, and then for 0 after initialization 0. Okay, so that is being followed. Okay, now what will be the scope after you exit the parallel block? Okay, so this is where we exit the parallel block, right? Hash pragma OMP parallel. Then after you exit this one, again the scope for x is unspecified. Okay, because let us see what is the value for x after exit. It's basically 10 because it is kind of not specified. Whatever is there will be because we don't know whether it should take a value of 30, 20, 0 or something. Let me try to run this again. Okay, it seems to be taking a value of 10. It could be because of, but it is certainly not specified as such. Okay, so according to the standard, that means the value of a private variable is unspecified at the beginning of the parallel or parallel for block. Okay, similarly the value of the of a private variable is unspecified at the exit of the parallel block. Okay, at the exit from the parallel block. Okay, so that means we cannot rely on these values when we write a code. Okay, however, the value of a shared variable will be preserved both at the entry and exit from the parallel block. Okay, now again, if it is not updated within the parallel block, if a shared variable is updated within a parallel block, then that updated value will be preserved at the exit from the parallel block. Okay, so that is how these private and shared variables behave in terms of preserving their values when you exit and when you enter the parallel blocks. Okay, all right. Okay, so I have a corresponding Fortran code as well, which I would like to show you. So if I go to Fortran, like codes, program private variables. Okay, so I have a corresponding Fortran code in which basically we have a main program, and then use OMP lib will basically include the OpenMP header files. Then I have X, and then unlike C, where we could actually define a variable just inside the parallel block, I could not define it in, because you cannot define variables after the executive statement starts. So basically I have to define only at the beginning. So I have my rank here as well as X that is declared at the beginning of the program. Okay, then we have the command line arguments that are being read here, and then if there is an error, it's going to print it. Then we have X equal to 10, and I have exclamation $OMP parallel num threads thread count. Okay, now again I have again I print its value before initialization, and I update the value of X using my rank times 10. Then we are going to print the value what is it after update, and then once you exit the parallel block, I'm going to print the value of X. Okay, now of course this program would not compile, it should throw an error because the behavior of, well, as of now it would not, because I didn't put default none, right? If I put default none, it would. So let me go here and then Fortran L8. Okay, so G Fortran minus F OpenMP program private variable. Okay, hash if def underscore OpenMP illegal preprocessor directive. That is coming because I have preprocessor directive, but I would use the C preprocessor. Okay. All right, so it's basically printed a couple of warnings, okay, which says it doesn't want me to write this comma here. I would remove this comma. Okay, and then I'm going to compile it again. Okay, it compiles fine. I say ./a.out. Say 4. Okay, it has printed something. Of course, this is not correct because now X is being both my rank as well as X are now because they are declared before the parallel block, they are taken as by default as shared variables, right? So that's why now all the threads, they are the my rank is coming out to be 3, and then whoever is what is the latest value, it's being updated and it's not coming out correctly. So what I would do is I would say default none, okay, and then I would say, okay, if I say default none and compile, it's going to give me error, right, which says my rank is not specified in enclosing parallel, as well as X is not specified, and then it basically gives 2 errors for each of these things, right? So I'm going to specify now private. So should X be private? Yes, X should be private. What about my rank? My rank should also be private, isn't it? So this is also private. So we have these 2 private variables. And what about any other variables? There are no other variables, so this is fine. Compile, no errors, then /error 4. Okay, now what we see is that before initialization we have my rank comma X are 0 0, so on 0 it is 0, and before initialization we have 1 comma 0, so it's basically not specified before initialization, and then 2 is also taken to be 0, and after initialization it's basically whatever is the 10 times the my rank is being printed, 1 10 0 0, and then once you exit, this value is not specified because it can be either 10 20 30, that is not specified. Okay, so that is the behavior which we reproduce even in the using the Fortran code. All right, now one thing you should see that because everything is compiled using OpenMP, the error that you get is pretty much the same whether you use a C compiler or a Fortran compiler, right? Because even in C it said a particular variable is not specified in enclosing parallel. Okay, so this is how you would get similar errors even if you are using different compilers, right? Because the underlying error is coming from OpenMP libraries. All right. Okay, so that is kind of consistent. All right, so that is about the scope of the value of the variables before and after the parallel blocks. Okay, let us now look at a little bit more about loops. Let me maybe change it to a little lighter version because this is too thick. Okay, let us look at more about loops. Okay, so we're going to take a closer look by using a couple of examples. Okay, so the first example we would like to take is I don't know if it is too thin. Okay, let us take a look at bubble sort algorithm. Okay, some of you might be aware of it. So basically this is a sorting algorithm. So if you have a set of integer values, if you want to arrange them in, let's say, in an increasing order, in an ascending order or so, you can use one of the algorithms that are available. Bubble sort is such an algorithm where similar to a bubble rising from the bottom of a water column, you would basically sort them the highest value towards the bottom of, in a reverse way. So essentially if you have a set of integers stored in an array, so this is an array, let's call this is an array A that stores n integers. Okay, and then it contains some numbers here, let's say, and then you have 0 1 2, these are the indices all the way to n. Okay, so what the bubble sort algorithm does is basically it's going to have 2 loops. The first one is basically going to select all the elements all the way to n. Okay, and then that means it's going to select all the n-1 elements here. The loop runs all the way here, and then it's going to basically compare these 2 values and then swap them if they are not in ascending order, and then after that it's going to compare these 2 and these 2 and these 2 and so on all the way, and then it is going to store the largest value in the n-1 or n, as per I have drawn here, 0 to n-1. Okay, this should be n-1 in the n-1 cell. Okay, and then it's going to basically compare up till n-2 and then store the next largest value in a-2 and so on. So as a result, once all the entire loop is done, you're going to basically get a sorted list. Okay, so what we do is basically write a corresponding serial algorithm and see if we can parallelize it using the parallel for. Okay, because there are a couple of parallel loops here. So the serial algorithm for bubble sort is basically you have for, if I have L equals n, L greater than or equal to 2, so essentially you would be comparing at least 2 elements. So you would stop if you have once you reach 2, because you would just compare these 2 and then arrange them, and then you would go L minus minus. So this is basically a loop that is kind of working with decrements because you want to store the largest value in n minus 1 and n minus 2 and so on. Okay. All right. Then you have another loop that is basically for loop for I equals 0, I less than L minus 1. So basically this is now depends on the outer loop value. Okay. So this depends on the outer loop value. Then you have I plus plus. Okay. Then the serial algorithm is basically if your a of I is greater than a of I plus 1, then you're going to swap a of I and a of I plus 1. So basically you're going to store a of I in a temporary variable, and then you're going to replace a of I with a of I plus 1, and then update your a of I plus 1 with the temporary variable that you have. Okay. So that is about the algorithm, and essentially it's going to compare the adjacent values. Okay, so it's going to compare these two values, right? And then if they are not in order, it's going to kind of swap them. So basically this is where the swapping is coming here, right? All right. So that is a simple bubble sort algorithm. Now let us see if we can kind of parallelize this using parallel for. Okay. One thing we learned about loops is that there is something called dependency, right? Or dependencies. We looked at two kinds of dependencies, something known as data dependency and another one is known as the loop carried dependency, right? We said that data dependency is not critical as long as we are accessing the same or different data that corresponds to the same variable I, right? Whereas loop carried dependency is something where the values of I are kind of dependent on I minus 1, I plus 1 or any other I minus, in general I minus some increment, right? This is where the problem comes in. So this loop carried dependency is the problematic part. Okay. That's what we have kind of discussed in the previous lectures. Okay. Now, is there a loop carried dependence in this one? Okay. Well, if you look at it, so we have two loops. So we have a outer for loop and we have an inner for loop. What about the outer for loop? Is there a loop carried dependence in the outer for loop? So, is there a loop carried dependence in the outer for loop? Yes, there is one, right? Let us say if you are dealing with essentially the contents of this A would change depending on the outer loop, isn't it? Because in one outer loop, in one sweep, you have certain elements, and then in the next one the elements are changed because you are swapping them. So as a result, so why I mean, when I say is there a loop carried dependence, what we mean to do is that if there is no loop carried dependence, we would like to kind of make this a parallel for, right? That's what we are interested in. Essentially, we are interested in parallelizing this algorithm. So as a result, if there is no loop carried dependence, we would like to parallelize this using parallel for. Okay, that means if you have, let's say, some 100 elements, we would like to write a parallel for which would make it 25 each on each thread. But what we see is that there is of course a loop carried dependence. If I take an example, let's say our A is now has 4 elements, let's say 3, 6, 1 and 2. Okay, so there are, let's say, 4 elements. Now what happens is that after the first loop L equals n, so L equals n is L equals 4, right? So you basically look at 0 to 3 and then it's going to swap them, right? So essentially what we do is in the first iteration 3 and 6 it will be compared here, right? It's going to compare 3 and 6 and they are in order, so there is no change. Then 6 and 1 will be compared, right? Because I equal to 0 is done, then you have I equals 1, and then 6 and 1 will be compared, and this will be made 1, 6, so you have 3, 1, 6, 2 after the first iteration. Then after another iteration, what you have is 6 and 2 will be compared, right? And then what you have is 6 is larger, so as a result, after the third iteration, you have 3, 1, 2, 6. Okay, so basically you got a the highest value, that is basically 6, is now at the nth location or n minus 1th location, right? Then of course the algorithm will proceed again, then the 3 will come to this position and so on, right? So that is how basically the bubble sort algorithm works. Now let us say, but the question is there loop carried dependence? Of course, yes, because the contents are changing, but then what would that mean? If there is a loop carry dependence, that means, let's say, if you, instead of running this using one thread, you want to run with using two threads. Okay, so basically you have thread 0, I would like to write T0 and T1. Okay, we have T0 and T1, and let us say it is going to split them into two parts. So thread 0 is executing list is 3 6, the other list is basically 1 2, right? So when thread 6 runs on this thing, it sees that this is already sorted, so nothing to do. And then when thread 1 looks at this is also sorted. So as a result, you basically have now, after one iteration, if you have used both T0 and T1 in parallel, then what you end up is, you end up with a 3612 as the iteration instead of 3162, right? Instead of this guy, you end up with 3612. As a result, now there is a possibility that 6, because let's say if you ignore the last element now, because it goes to n minus minus, right? So L minus minus, so that means you end up with 6 be basically the largest element will still be in the active elements of A. So this is not correct, right? So as a result, there is a loop carry dependence. Right, because essentially the loop carry dependence, we mean to say that as your elements are swapped incorrectly. As a result, the intended behavior is not obtained for the outer loop. Okay, so there is a loop carry dependence for the outer loop. Now what about the inner loop? Is there a loop carry dependence for the inner loop? What is the inner loop? Inner loop is the one that is basically this guy, right? This is basically for I equal to 0, I less than L minus 1, I plus plus. Of course, there is a loop carry dependence for inner loop as well. Yeah, but it may not be very straightforward. Yes, there is loop carry dependence. Now how do we see if there is a loop carry dependence for the inner loop or not? For example, let us say you are looking at a particular ith iteration, right? Because you have for I equal to 0, I less than L minus 1, I plus plus. Okay, so if I'm looking at ith iteration, let's say it is some I, then we are comparing AI and AI plus 1. Okay, but then what we are comparing, whatever we are comparing, the AI and AI plus 1, or in general the elements of A elements of A at ith iteration, right, would depend on the whatever is done at the I minus 1th iteration, isn't it? Because we are kind of swapping. So that means, let's say in the I minus 1th iteration, I minus 1 and AI are swapped. Okay, that means your elements will be AI and AI minus 1, right? This is how your new elements will be. Now when the ith iteration comes, then it's going to compare AI minus 1 with AI plus 1, right? Because it's always going to compare I and I plus 1. So this is how it's going to compare. Now if these were not swapped in the I minus 1th iteration, then your elements will still contain to be AI and AI. Then if they are not swapped, then the elements will be AI minus 1 and AI. It will remain like this in the after the I minus 1th iteration. That means when you enter with ith iteration, then the elements you will be comparing will be AI and AI plus 1, right? So that certainly there is a difference, right? In the first case, you have AI minus 1 and AI plus 1 are compared, whereas if they are swapped, AI and AI plus 1 are compared, right? So as a result, there is a loop carry dependence. Okay, that means if you because the contents of A would depend on at any ith iteration will depend on what happened at the I minus 1th iteration. This is essentially similar to your Fibonacci series, right? Unless you know what has happened before, you won't be able to compute the value at the current iteration. So as a result, there is a loop carry dependence in the inner loop as well. That means if you try to apply for essentially for this for loop, if you try to make it parallel, it won't come out to be correct, because AI minus 1 that are swapped in one thread may not be reflected in the other thread, and it will be working with something other, some other value. So as a result, the inner loop also cannot be easily parallelized. Okay, so that means, and it is also not clear how actually we can easily remove this loop carried dependence unless we rewrite the algorithm completely differently from a different perspective. Okay, so that means it is very important to keep in mind that we always find, or we may find, loop carried dependence, and it may or may not be possible to remove it all the time. Okay, so loop carried dependencies are often encountered, and it may or may not be possible to remove them. Okay, so to kind of state it differently, the parallel for directive is not a universal solution, okay, to the problem of parallelizing loops. Okay, so that means we have to remember that parallel for is not a universal solution for parallelizing loops. That means if you have a loop, it is not that you just make it parallel for and it would run on, it would kind of run on its own. So that means it's not a universal solution. Okay, so let us see if there are any other alternatives which we can easily parallelize. So let us take another example. The other example is known as called as odd even transposition sort. Okay, so this is basically another sorting algorithm. Okay, kind of similar to bubble sort. However, in the odd even transposition sort, you have essentially more opportunities for parallelizing the code. Okay, so what is odd even transposition sort? So basically, in the odd even transposition sort, you essentially look at several passes. Okay, you go through the list of A that you have several times. So you basically go through pass 0, pass 1, and so on. So you do different passes, and each traversal or pass you are going to look at a list separately depending on whether you are looking at an even or an odd iteration. Okay, or even or odd pass. Okay, so depending on that, you're going to do things differently. So if you are at a even pass, you are going to basically compare your ith element to the I minus 1th element, and you're going to swap them if required. And if you are at the odd pass, you're going to compare element to your right, that is ith and I plus 1, and you're going to swap them if it is required. Okay, so that is how essentially the odd even transposition sort would look like. So I would kind of quickly write a small code here, kind of a serial code, and let us see if there are any loop carried dependencies that exist which will kind of prevent us from parallelizing this code or not. Okay, so basically similar to bubble sort, you have two for loops. You have for the pass is the one which is the outermost for loop. You have pass 0, pass equal to 0, pass less than n, and then pass plus plus. Okay, and then you have if your pass is a even. Okay, essentially you're looking at a even pass. Then essentially you will look at you will loop over the elements for I equals 1, I less than n, I equals I plus 2. Okay, so this is critical here. Okay, because we are swapping, we would look at I equal to I plus 2, not I plus plus. Okay, and then what we do is, if element to the left is higher, let's say if a of I minus 1 is greater than a of I, then what you're going to do is you're going to swap a of I minus 1 and a of I. Okay, otherwise you're going to leave it as it is. That means if it is a odd pass, then you are still going to, for I equals 1, I less than n minus 1, I equals I plus 2, and you're going to look to your right. If a of I is greater than a of I plus 1, then you're going to swap your a of I ampersand a of I and ampersand a of I plus 1. Okay, so you're going to swap these two. So that's basically your simple algorithm for odd even transposition sort. Okay, now of course there is a particular theorem that guarantees that after n passes, the a of n, okay, this array that contains the integers will be sorted. Okay, so there is a theorem that guarantees that, and we are not looking at those parts. That we are not looking at the theorem and the proof and all as part of the course. Okay, we just take the algorithm and see if there is a loop carry dependence or not, so that we can go ahead and basically parallelize this code. Now again, how many loops do we have? We have essentially 3 loops, but out of that only there are, if you talk about, there is an outer loop, and then there is one inner loop. I mean, there are 2 inner loops, but they are like kind of mutually exclusive depending on the path. So in general, we have 1 outer loop and 1 inner loop. Okay, now let us see if there is a loop carry dependence. So is there a loop carry dependence in the outer loop? Is there a loop carry dependence in the outer loop? Well, you have pass 0, pass n, pass plus plus. So what about the contents of a of I? Contents of a of I are changed inside. That means every pass, at any pass, we have the contents would be different depending on what happened before. So as a result, we can say that there is a loop carry dependence in the outer loop, right? So I can say that there is loop carry dependence for the outer loop. Okay, now right, so that is what we have. That means, well, let me take an example and explain. Let us say we have A contains 4 elements. Let's say we have 9, 7, 8 and 6. Okay, this is not in the right order. So in the pass 0, what would happen in pass 0? You enter here, pass 0, you have pass person 2. So this is basically even. I equals 1, I less than n, I equal I plus 2. You're going to compare elements to your left. So A0 and A1 are compared. So that means A0 and A1. That means 9 and 7 are compared, and they will be swapped. So you essentially end up with 7 and 9. Okay, and then I equal to I plus 2. So I equals 3. So basically 8 and 6 are compared in the same in the loop, right? So and then this is basically made into 6 comma 8. Okay, so that is after pass 0. Now once you finish I equal to I plus 2, then I equals 5 will exit from the loop because n is 4. Then you go back and then you go to pass 1, right? So pass 1 is not even, so it's odd, it comes here. I equals 1, I less than n minus 1, I equal to I plus 2. Swap element towards your right. That means in the pass 1, what we would do is, you're going to now look at 1, right? A of 1, that is 7 and 8, right? So you're going to look at elements 7 and 8, and these are already sorted, so you don't have to do anything. And then when you do I equals I plus 2, you essentially end up with 3, right? So now the list is already so you're going to look at so this is the list, right? So 7, 9, 6, 8. So you're going to look at 9 and 6, right? 9 and 6, and then 9 and 6 are not in order, so you're going to swap them to 6 comma 9. Okay, and then you go to I equals I plus 3. So I equals 1, I equal to I plus 2. So essentially you end up with 3. So 3 is your so your new list is now, what is the new list? You basically have 7, 6, 9, 8. So you're going to look at 9 comma 8 and then swap them to 8 comma 9, right? So basically you already end up with 9 in the right place. Okay, so this is after pass 1. Okay, so that's what you have. Now let us say we try to parallelize the outer loop. Okay, that means we are running the outer loop on 2 threads, thread 0 and thread 1. That means thread 0 gets 9, 7 and thread 1 gets 8, 6. So there is every chance that after while pass 0 is working on, right, that means while pass 0 is being given to thread 0, pass 1 may be given to thread 1, and thread 1, instead of working with this 9.6, it would still be working with, right, 7.8, right, because 7.8 is what it sees as the original elements, right, because it is the thread 0 might not have completed the swapping. Instead of making it 7.9.6.8, instead of working with thread 1 working with 9.6, it would still be working with possibilities that it may still work with 7.8. So as a result, we can see that there is a loop carry dependence on the or in the outer loop, right? Okay, that means there is nothing great about odd even transposition in the outer loop when it compared to the bubble sort. So we can't really gain anything there because we cannot parallelize it easily. Okay, then what about the inner loop? So you have two inner loops, so basically this one as well as this one. Now what about let's say first inner loop? If pass is even, then I is odd, I equals 1, I less than n, I equal to I plus 2. That means if you try to parallelize this one, what would be the values that will be given to I? So I will go to 1, 3, 5 and so on. So basically I is going to get 1, 3, 5, 7 and so on. So if you take two elements 5 and 7, so I equal to 5 will be comparing 4 and 5, right? And I equal to 7, if it is given to a different thread, it will be comparing 7, right? It will be comparing, so this is how it will be going. That means the other thread, which will basically be talking about yeah, so you already have 6 also is here, right? I mean, I just put this as odd numbers, but then the other value will be 7, right? 7 will be comparing 6 and 7, right? That means you'd have independent array elements that are being accessed. So as a result, there is no conflict here, and the same is the case here, right? Because you are comparing I and I plus 1, it is jumping by values of 2, right? Increment is by 2. You will be comparing with different indices in the inner loop. So as a result, the inner loop does not have loop carry dependence, right? And it can be parallelized. Okay, that means the outer loop cannot be parallelized, whereas the inner loop can be parallelized. Now there is of course one catch here. The catch is that although inner loops can be parallelized, their contents should not be changed, right? These threads should not go forward and execute a different pass, right? So that means the pass should be the same, and within that only we can parallelize these two for loops, right? Because the content should not be changed with a different pass, and that is not valid. As a result, we need a kind of a barrier here, such that only once all threads have finished, the contents of A can be changed in the next pass. And that is very much guaranteed if you have a parallel for or a parallel block, because there is an implicit barrier at the end of parallel block as we saw before, and there is also one in the parallel for also. Okay, so it appears the correct way to parallelize the odd even transposition is to have kind of parallelize the two for loops that we have inside the main loop. So if you were to parallelize, so it is basically like this. So you have for pass equal to 0, pass less than n, pass plus plus, okay, and then if you have if pass is even, right, then you would basically parallelize hash pragma OMP parallel for, and you have num threads something, okay, and let's say we use a continuation operator, and then we want to also make use of this default clause or default none, and then what are the shared variables we have and what are the private variables. Okay, so what are not being what can be shared? Can A be shared or A should be private? A is, because there is no there is no conflict, because none of the threads are updating the same location. A can be shared, and right, so A can be shared, and what else can be shared? N can be shared as well, right? N can be shared. Whatever the private values will be I will be private, what else? And if you have some temporary array that we have used before, so basically that also can be private, right? Because the temp also should be private. And then once you have a parallel for, it should be followed by a for loop. So you have for I equals 1, I less than n, I equals I plus 2. Okay, that is fine. And then if you find yourself, if a of I minus 1 is greater than a of I, then you basically would swap temp equals a of I minus 1, a of I minus 1 equals a of I, and a of I equals temp. Okay, that's what we have. If not, so essentially this is the end of the for loop. Then we have the pass this one, so this is basically else we have another for loop, right? That's basically hash pragma OMP parallel for, and you have num threads count, and then just like before we have default none, and then you have shared a comma n, and then you have private I comma temp. Okay, so that's basically I comma temp. And then you have your for loop again, for I equals 1, I less than n minus 1, I plus equals 2, or I equals I plus 2, and then you look for your right. So if a of I is greater than a of I plus 1, then you're going to swap them, right, using the value of using the variable temp. Okay, that's what we would do. And then you end the for loop, and you may enter the and the pass loop as well. Okay, so that's what we do. Now, of course, as we discussed, there is an implicit barrier. There is an implicit barrier here. Okay, in the parallel, in the for each of the for loops. So there are so there is an implicit barrier here as well as implicit barrier here. Okay, in the parallel for loops. So as a result, the pass is not going to the next. Whatever the pass at p, it would not go to p plus 1, p plus 2, and so on, all the way to n. It would basically wait for all threads to finish one pass and then go to the next pass only. So that is one issue which we can easily see, which is already addressed by the behavior of the parallel first. Now, what is the other issue? The other issue is that, as you can see, we have a for loop, and within the for loop we are forking and joining the threads, right? Essentially you have a for loop, so every for loop, for every pass, we are forking the threads and then we are joining them again, and then we would do it again and again. So that is kind of, there is a little bit of overhead associated with that. To avoid that, what we can do is we can put this, move the hash pragma OMP parallel, only this part, outside the pass, outside the for loop here, so that the forking is done here, and we can simply write hash pragma OMP for here. So what you can do is you can basically write hash pragma OMP parallel here, and then when it comes to this location here, we would write hash pragma OMP for. So that means OpenMP for, so that the four threads are already here, and we are not changing the number of threads from pass to pass. As a result, we can move that out, and then you can just write hash pragma OMP for here, and then declare all the variable scope in the outer location here. And that way we don't have to worry about the overhead, because now the threads are forked once, and once all the passes are finished, they are going to be again joined. So, and then within the for loops, for each of the for loops, they will be executed using parallel for with the already forked threads. Okay, so that will kind of save some overhead that we may get. Okay, so what you would do is basically you would move I would just repeat it here. So you would write hash pragma OMP parallel. So you are creating a parallel block, not a parallel for at the moment. Num threads, give thread count, and then you basically have default none, and you have shared a comma n, private I comma temp comma. Now of course you need to also make pass as a private variable, because pass is now also comes, because pass has to be private. I mean, even if you don't give it, it will be taken as private. but because this is not a for, it may not take it. Okay, so that you need to check, so verify that whether it is working or not. Okay, and then you have the for loop for the passes, and then when it comes to the inner for loop for I equals 1, I less than n, I equals I plus 2, you would put in here simply hash pragma OMP for, that's all. Okay, because so for is the keyword, is the class, and then essentially the threads are forked outside the pass and they would be joined once everything is done. Okay, here the OMP for is going to work with already existing threads. Fine. Okay, I think that you can easily check. And so this is how we can parallelize odd even transposition, which is kind of an alternate method compared to bubble sort. Okay, so there is some opportunity for parallelization in this particular sorting algorithm. Now these two are just a couple of examples. You may run into a different kind of problem. Excuse me. If you may run into a different kind of problem in your when you try to write your own code for your project or for your research, then you have to selectively kind of decide whether it is possible to parallelize a particular loop or not, or should you just run it in serial and things like that. Okay, we will probably get some opportunity to look at this when we look at the numerical methods part of the course as well. Okay, so I'm going to stop here for now. I'm going to we will catch up from here in the next class. Okay, thank you.